Hey guys, welcome back to my channel. It's a little bit of a different kind of video today. So I was trying to do my homework and it included the method of solving truss displacement using like virtual forces and virtual work. And so I could not find a single video that had a straightforward explanation of how to actually solve one of these problems and wasn't talking about like integrating or whatever. So once I figured out, I thought I would help you guys try and solve these too. So we're going to be just using an example from Pearson today and learning how to solve these. But first, let's go up and look at like what are the actual equations that we need. So there's 3 different equations for like a truss type situation, and one has to do with just like an applied force, which is this first equation here. The next one has to do with temperature change, and the next one has to do with fabrication errors. So when they say fabrication errors, they mean if a beam was made shorter or longer than it was supposed to be. So all of these equations are pretty similar, and in some cases, you will have to add up. So all of these have this sum symbol right here, right? So in some cases, you might have to add up different of these right sides of these equations for one beam, but we're just going to be doing an applied force one today, so we're going to be using this equation. And it has a lot of different things in it. So we have some recognizable things like A and E, so modulus of elasticity, cross-sectional area of beams, length of the member. And so N is internal force, as in if you solved a truss problem and found the internal force caused by a real load. And N is internal force caused by a virtual load, a virtual unit load, which is kind of like weird, kind of abstract concept. So we'll go over that really quickly. And then just some conventions down here. Positive is tension, negative is compression, and then for our other equations like change in temperature, we have those here too. But our method of solving here, we're going to have steps. So step 1 is we're going to place the virtual load where you want to measure displacement, and I'll show you guys how to do that in a second. We're going to remove the real loads and solve that truss problem with just the virtual load. So the virtual load always has magnitude of 1, and it basically gives you can think of it as giving you a percentage of how much each beam is going to go down at that one spot, right? And it allows us to scale our other loads. And then number 4 is we're going to solve just our regular truss problem using our actual loads. And number 5 is we just plug those values into our equation. So let's go up here. I'm going to copy this equation because it's the one that we want. And then I'll show you guys how to solve this example problem. So this example problem has given us oh dear God, I don't know what I've done there. Anyways, this example problem has given us a truss made out of A992 steel. Oh my goodness gracious. And having a cross-sectional area of 4.5 inches squared. And so, and they want the displacement in inches at B, I think. Let me check. They want, They want the vertical displacement of joint E. So they want the displacement here. So how much is it going to go down by? Because, we've got an applied load downwards. We can probably guess that it's going to be down. Okay. And so let's just write down what we know. And they want it in inches. So let's just choose our units right away so that's all going to work out. Okay, so we have a cross-sectional area of 4.5 inches, so that's going to be our A here. So A equals 4.5 inches squared. And our loads are in kips. So kilopounds, so 1,000 pounds. And so let's go find our E in whatever they're called, imperial units, maybe stupid units, I like to say. So our E in imperial units is 29,000 KSI, which is kip per square inch. And so this means that when we take our lengths, we're going to want to take these in inches, not feet. Okay, so we're going to want to do everything in inches and kilopounds, and that way it will work out perfectly. So step one is probably the most confusing and the one you haven't done before, is we want to be able to solve this problem. We want to be able to solve this virtual applied load problem, which is like, what the crap is going on? So we have our truss member here. And we have F, E, D, C, B, A. And then we're going to have applied load. So our applied load is always going to go, in the direction that we want to measure displacement, and it's only got a value of 1. It's always going to have a value of 1. There's no calculations you have to do here. You just have to put it where you want to find the displacement, which in this case is the E, and in the direction, obviously it's going down, and what the value is always going to be 1. So now we just have a really simple truss problem, right? So we know that, and if you know how to solve a truss and you're confident in your truss solving abilities, you can go ahead and skip ahead here because this is a lengthy problem, right? But we know that we have a pin reaction here at C, so we can only have one reaction upwards. And then we have it's a roller at C and a pin at A, so A is going to have 2. And so how do you think we should solve for that reaction at C? Well, we know the distance here is 8 feet. And, well, we can just take a moment about A, and then we'll be able to find a reaction at C. So a moment about A is created. We've got E, so 1 times 8, and then we're going to divide that by 16 to find a reaction at C. So we're going to have a 0.5 reaction at C, and because there's no horizontal reaction here, we know that we're also going to have a 0.5 reaction at A to add up to 1 here. So let's start trying to solve this member. So we know that, let's start making a list over here. Virtual. We know that BE must equal 0. And how do we know that? Well, if we zoom in on this joint here, if we zoom in on joint B, we have what looks like a 0 force member, right? Because this can't equal anything, or else we have 2 horizontal beams that are supposed to support a vertical load, which is impossible because these have no upward component. So we know that BE equals 0. Next, let's try and solve for some of the other ones. Let's look at these joints here. These also look an awful lot like 0 force members, right? Because we have F, we've got two beams coming at a right angle, and they have no applied forces to them. So if I have a horizontal force in FE, is there any possible way that this vertical beam FA can counteract that horizontal force? And the answer is no. So that means FE must equal 0. And AF must also equal 0, because if I have a vertical force in AF, there is no possible way that this perfectly horizontal beam FE could ever counteract that vertical force. So FE equals 0, FA equals 0, and we can say the same for the other side. ED equals 0, and CD equals 0. So this is looking like a really nice problem. We're just going to go ahead and put a cross through all these nice zero force members. Now let's look at E now. Okay, I think this one we can go ahead and probably solve now, right? So we have joint E. Goodness gracious. We've got joint E, and we know that it's basically just got two beams like this and one downward force, magnitude 1. Well, let's think about this, right? This is 6 feet tall. We basically can assume that these two are equal, because anything that this one does horizontally has to cancel out the other one, and vice versa, and they're the same geometry. So these two are going to be equal. So we know that the vertical force in one of these, let's just make our little triangle here, and it's going to be in compression. So we know the vertical force in one of these is going to be 0.5, and that the horizontal force is going to be equal to whatever the other one is. But because we know that this is, and let's just look at our thing. So it's an 8, 6, 10 triangle, but that's the same thing as a 3, 4, 5 triangle. So if we have 0.5 divided by 3 times 4, that will give us our horizontal, right? So let's do the math. 0.5 divided by 3 times 4, it's going to give us 0.66 horizontal, and times 5, 0.5 divided by 3 times 5 is going to give us our hypotenuse, which is going to be 0.83. So we know that AE and remember it's in compression, so it's going to be negative. So negative 8.3. And CE is going to be negative 0.83. And now we just have two more non-zero beams members to solve for, which is AB and CB, which luckily for us are also going to equal each other, right? And if we look at this triangle here, right, so this is the same thing that's coming in. This thing here is the same thing that's coming in to joint A. So we can draw this at joint A. We know we have 0.5 up, and we're just going to draw this split up because it's going to be so much easier, right? So we've got 0.5 up, and it's pushing on it, right? So it's in compression. So we're going to have 0.667 going sideways, and we're going to have 0.5 going down. So those 0.5s are going to cancel, and that means our beam coming out, as in AB, has got to be in compression 0.667, and the same goes for CB. Okay, so that's our virtual member solved. It's not exactly simple or easy. Well, yeah, I think it's a simple process, right? We all know how to solve trusses. It's not quick, it's not quick and easy, but I think you all are capable of solving a truss. And so now we just have to solve our real truss. So let's look up here. Our real truss doesn't have any applied force at E, but it does have an applied force at B. So let's just kind of, I'm just going to draw a new one because, so let's reel. Right, we've got this. And our reaction forces are going to be different this time because we've got different forces. So we've got 1 here, we've got 2 here, and let's just label these just for good measure. So we've got A, B, C, D, E, F, I think. And then we have an applied force downwards of 5 kip. So we have 5 kip down, and let's just put some 8 feet, 8 feet, and 6 feet. Oops. And so some of these are no longer going to be zero force members, right? So these ones still don't have any applied loads on them, right? There's no way that those can have any force in them. So those are still going to be 0. So we're just going to put a cross through those. But this one right here is not going to be 0 because now we have an applied force. So when we have B with a downwards force like this, it goes 5. We know that the upwards one has to be 5 kilopounds as well. So we can tell right away that EB is going to equal 5 kip in tension. So now that we know EB, we can go ahead and figure out, we could solve for our reactions at A and C, or we could go ahead and solve E and then just solve that way. Let's do it a little differently this time. Let's just go ahead and solve at joint E and skip solving for the reactions, because you'll find that we actually are able to just not really pay attention to those because we only have horizontal beams here, right? Those are not going to have any vertical component. So if we really wanted to know our reactions, we could find it from the vertical component of this beam, but we don't really need those here. So let's solve for joint E. So E, once again, we only really have, we have these ones, and then this time we're going to have 5 kip going down. So we know, oops, I think I did something wrong on my last one. No, I didn't. JK. So we know here that our vertical ones, right, they're going to have to support 2.5 kip here. And we know that this is still, you know, a weird 3, 4, 5, right? It's still a 3, 4, 5 triangle. So we've got 4, 3, 5. So if we do 2.5 divided by 3 times 4, we'll get our horizontal part. And that's going to equal 3.3. Hey, stop that. Hopefully I can finish this before my Apple Pencil dies. We'll see. And then our vertical one is going to be 2.5 divided by 3 times 5, which is going to equal 4.16. So we know, and this hypotenuse, right, is, looking back at our diagram here, this is AE. In compression, so it's going to be negative. And we know that CE is the same. So CE equals negative 4.16. Going down to our joint A here, we can know that this is the same force right here that can be broken up into the same vertical and horizontal components, right? And so we know that there's only one horizontal force coming into A that can cancel out the 3.3 in compression here, so we know that our horizontal forces have to be 3.3 kips in tension. So that means AB equals 3.3 kips, and BC also equals 3.3 kips. And then we'll be able to go plug this into our equation. So, hard work now, and now we just have to plug it in, right? So we've got real, and let's go grab our virtual ones. Holy crap, that's a lot of numbers. Copy. And then let's go grab our equation, right? We're going to probably want that. And I hope it doesn't copy. I'm just going to go all the way to the top and grab it, right? Let's hope it copied. All right. Okay, so this is an equation that's a sum, right? So this means for every beam, we have to do this equation. But the great thing for us is that most of these beams are going to be times 0 in this n part, right? This virtual load is what corresponds to the n. So those ones that are times 0, it's going to make the whole equation 0. So we can just ignore those. And really the only one here that matters is the BE. Yeah. I'm not going to ignore that because, right, it's 0 here. So we don't need that value. So this turns into not too bad of an equation. So let's just make this. So let's go our deformation at, or our change in whatever, at E is going to be equal to, just a little subscript here. Let's do AE first, right? Is going to be negative 4.16, and keep your negatives, even if you think, well, those negatives cancel out, it doesn't matter. Don't just make a negative because you think you feel like it. If the negatives cancel out, it's for a good reason. Okay, so we have our, maybe I'll do it in the order that follows. So we have our little n for AE equals 0.83, our big N equals negative 4.16, and our length, now remember we're doing everything in inches and kilopounds, so our length of AE is not going to be 5 feet. We're going to do 5 feet in inches. So let's find 5 feet in inches. So 5 times 12 equals 60. So 60 inches. I should probably put inches, but it's okay. And then we're going to divide that by AE, which is going to be the same for all of these, which is going to be 4.5 times 29,000. Okay, now let's do our next one. Here, I'll highlight it in a different color. So we're going to go plus little n, so negative 0.83. Oh, hey, guess what? This is going to be the exact same equation. Look, we've got the exact same numbers, exact same symbols. So we can just do AE and CE. Right, we can just do 2 times this equation. Isn't that nice? And look what's going to happen. With our next one here is that these next two are also the exact same sign, exact same number. So we can also just do 2 times. Right, our little n is going to be 0.667. Big N is 3.3. Our length, AB and BC, are the same, so 8 feet, which equals 8 times 12, 96 inches. And then we're going to have over that same 4.5 times 29,000. And let's see what answer we get. And we're going to get 0.00641 1 inches. Let's see if we got the right answer. Shit. So, I've done something wrong. I'll get back to you guys in just a second when I figure it out. Hey guys, I'm back. So this is the actual correct answer. And the mistake that I made is that I thought AE and CE were 5 feet long, right? But they're actually 10, right? It's our 3, 4, 5 triangle, but it's double the size. So it's not a 3, 4, 5, it's a 6, 8, 10 triangle, right? So that's my small mistake there. But this is your real answer that you should get. It's the answer that Pearson gets. And they want, you know, we had our arrow pointing downwards, right? We know that it's going downwards, but they want us to represent that with a negative. So they say negative this many inches if it's going downwards. I hope this helps you guys. I hope this is a clearer understanding and helps you guys actually be able to solve problems. And let me know if you want me to do more videos like this. All right, have a good time, guys. Bye.